In 14.3, I'm going to discuss the law of conservation of momentum and collisions. We'll start with an example. Here, a 1,000 kilogram car is traveling at 6 meters per second when it collides with a 2,500 kilogram truck that's initially at rest. The collision results in the car experiencing an impulse of 4,000 kilogram meters per second. Part A wants us to calculate the car's momentum and the direction of motion after the collision. So when the car and the truck collide with each other, they're going to exchange forces. The truck will exert a force on the car backwards. That same force is going to be exerted forwards on the truck. These two forces complete a action-reaction, Newton's third law force pair. The impulse on each car is going to be in the direction of that force. So the car will experience a backwards acting impulse, and the truck will experience a forward impulse. So focusing on the car, the impulse is the change in the car's momentum. And the change in the car's momentum is its final momentum minus its initial momentum. So the car experiences an impulse of 4,000 kilograms, but we have to account for direction. I'm going to make the right direction positive. So the impulse on the car is going to be negative. And that'll equal the final momentum that we're trying to calculate minus the initial momentum. And we know how to calculate momentum. It's mass times velocity. So the mass of the car is 1,000 and the velocity is positive 6 because the car is initially moving to the right. That makes its initial velocity positive. And when we calculate the final momentum, we end up getting 2,000 kilogram meters per second. And since we got a positive value, this means that after the collision, the car is going to continue moving to the right, which is its direction of motion. Now, part B wants us to calculate the speed. If we know the momentum and the mass of an object, we can just calculate the speed with this. The momentum is 2,000. The mass is given as 1,000, and so the speed is 2 meters per second. Now, in part C, we want to know the truck's momentum and direction of motion. So again, we're going to go back to impulse. Impulse is change in momentum, and the change in momentum is the final momentum minus the initial momentum. And since the truck starts from rest, the initial momentum is 0. So the final momentum is equal to the impulse that the truck experiences, and the truck experiences an impulse to the right, so positive, 4,000 kilogram meters per second. This number and this number are going to be important later in this example, so keep these numbers in mind. The truck ends with 4,000 and the car ends with 2,000. And part D wants to know the truck's speed. So again, we'll use momentum is mass times velocity. We have a momentum of 4,000, a mass of 2,500, and that gives us a speed of 1.6 meters per second. So this is important here. We have this situation where two objects are colliding and they exchange forces. And because those forces are making up what's called a Newton's third law force pair, equal and opposite forces, then we have an important consequence of this. It's conservation of momentum. If we have a system where there are no external forces acting in a way where there's an external net force, then internal impulses will always cancel. And if internal impulses cancel, that means the total impulse on the system is zero. And if the impulse is zero, that means that the system does not change its momentum. And if the momentum does not change, that means it is constant. And when something is described as being constant, it is described as being conserved. So we have arrived at what is known as the law of conservation of momentum, where if we have zero impulse, that is the result of zero net forces coming from outside external to our system, then the total momentum of our system is going to be constant before and after a collision, or the opposite of a collision is an explosion, then the momentum is going to be constant. So remember I said those two numbers are important? Well, what's the momentum of the car truck system prior to the collision? Well, prior to the collision, we only have the car moving, right? The momentum of the system will be the momentum of the car plus the momentum of the truck. The car has a momentum equal to its mass times its velocity, or 6,000 kilogram meters per second. So the system started with 6,000. Well, how did it end with? Well, what's the final system momentum? This will be the momentum of the car, final, plus the momentum of the truck, final. Well, we had those on 2 slides ago, and the momentum of the car to end with was 2,000, and the momentum of the truck after the collision was 4,000. We started with the same momentum that we ended with. Therefore, momentum was conserved in the collision between the truck and the car. In this example, we have a 2 kilogram pistol with a 20-gram bullet inside. And the pistol and bullet are initially at rest. After firing, we want to know the momentum of the bullet pistol system. Well, there are no external forces acting on the bullet pistol system. Therefore, the momentum of the bullet pistol system has to be conserved. Well, initially, neither object was moving, and so together they had no momentum. An object that's at rest has no momentum, so a system at rest also has zero momentum. So the momentum is going to be zero both before and after the pistol is fired. What's the momentum of the bullet after it is fired? Well, this is pretty straightforward. Momentum is mass times velocity, and the mass is given as 20 grams, but we want to make sure that we're in consistent units. So 20 grams is 0.02 kilograms. And you can see in the graphic that the speed of the bullet after firing is 150 meters per second. Multiply those two together, and you end up getting 3 kilogram meters per second. So what's going to be the momentum of the pistol? Well, the total momentum, which remember was zero, would be the momentum of the bullet plus the momentum of the pistol. So how can two momenta add up to zero? Well, for them to add up to zero, the momentum of the pistol would have to be equal and opposite to the momentum of the bullet. If they have equal and opposite momenta, they can both add up to zero. So the momentum of the bullet was positive 3. Therefore, the momentum of the pistol would be negative 3 kilogram meters per second. And we can calculate the speed of the pistol. Mass times velocity. We know the momentum is 3. We know the mass is 2. Therefore, the speed is 1.5 meters per second. It is backwards, but it was asked for a speed. All speeds are positive. And I do want to point out that the mass of the the mass of the pistol divided by the mass of the bullet is 100. The pistol is 100 times the mass of the bullet. The mass and the velocity are inversely proportional for the same momentum. Therefore, that's why, if you notice, this speed is 100 times less than the speed of the bullet. Since there's a ratio of 1 to 100 in mass, there is going to be a ratio of 1 over 100 for the speeds. Speed of the bullet will be 100 times the speed of the pistol. All right, now what about the energies? We talked about momentum. What about the energy? So we can calculate the energy of both of these objects by taking 1/2 mv squared. So the kinetic energy of the bullet, when we multiply this out, is 225, and that's in joules. So what about the pistol? Well, the pistol has a mass of 2 kilograms and a speed of 1.5 meters per second, giving it a kinetic energy of 2.25 joules. And notice that these have a ratio of 1 to 100. So when we total these up, the total is 227 and a quarter joules. Where did this energy come from? Well, in firing the bullet, there is a combustion reaction with the gunpowder that releases energy. It had stored up energy. Well, in part F, it asks why are we able to safely handle the gun when it's fired? After all, somebody's holding the gun, while the bullet is really dangerous. Well, it comes down to energy. They had the same momentum, but they have very different energies. Same momentum, but the bullet carries an energy that is 100 times greater than the pistol. So it's the energy that is what makes the bullet dangerous, but the pistol not so dangerous. Okay, and in our last example, we have a 90 kilogram running back. In our last example, we have a 90 kilogram running back that's running with a speed of 4 meters per second when he's met by a 100 kilogram linebacker running at 4.5 meters per second who performs a head-on tackle. Part A wants us to find the total momentum of the running back linebacker system prior to the collision. So, to find the, come on, really? In our last example, we have a 90 kilogram running back that's running with a speed of 4 meters per second when he is met by a 100 kilogram linebacker running at 4.5 meters per second who performs a head-on tackle. Part A wants us to calculate the total momentum of the running back linebacker system prior to the collision. So to find the momentum of the system, all we have to do is find the momentum of both players and then add them together. So momentum is mass times velocity. I'll make the running back object 1, and he has a mass of 90 kilograms and is moving with a velocity of 4. I will make the right my positive direction. So he will have a momentum of positive 360 kilogram meters per second. The second player, his momentum will be his mass, which is 100 kilograms, times his velocity, which is in the opposite direction, so it has to have the opposite negative sign and he has a momentum of 450 kilogram meters per second. The total momentum is just the sum of the two momenta, and when you add them up, you end up getting 90 kilogram meters per second in the negative direction. So together, they have a momentum that is in the negative direction. Part B wants us to find the total kinetic energy of the system prior to the collision. So finding the kinetic energy of the system is going to be a very similar calculation. We'll find the kinetic energy of each player individually, and then we're going to add them up. So the mass of the first player is 90. He's moving with a speed of 4, and so he has 720 joules of kinetic energy. The defender, who has a mass of 100 kilograms and is moving with a speed, not a velocity, a speed of 4.5, he has a energy of 1,012.5 joules of kinetic energy, and we can add that up to find the total kinetic energy of the system is 1,732.5 joules. Part C wants to know with what speed do the two athletes move together after the collision? So for part C, the system started with negative 90 kilogram meters per second. So that total momentum has to be maintained. After the collision, they're going to move together as though they are one object moving with some common speed, common velocity rather. And so the total momentum, which has to be conserved, is still negative 90, but now they're going to move like one single object with a combined mass of 190 kilograms, and they're going to be moving with a speed of 0.474 meters per second. Now, this is just the speed. We should note that after the collision, they're going to move to the left, and they're going to move together. This is just the speed of the two players together. And for part D, well, what about the kinetic energy? Well, again, kinetic energy is a half times mass times speed squared. Again, they're moving like a single object with a combined 190 kilograms of mass with a common speed of 0.474 meters per second. So after the collision, we have a kinetic energy of only 21.3 joules of kinetic energy. So in this collision, what happened to that energy? The energy that we originally had up here, most of that energy went into sound and heat, and a little bit of it went into sort of rearranging the anatomy of these players. Anybody that's ever been hit really hard knows that your body's not quite the same as it was afterwards. And our bodies are not elastic. They don't go back into the exact same shape. So we will lose a little bit of the energy in this sort of collision, which I should point out is the opposite of the last example where there was a release of energy. In an explosion, there's always an increase in the total energy. In collisions, there's always a loss of kinetic energy.